Let's wrap up our unit on magnetism. Let's look at a bar magnet. A bar magnet is a permanent magnet that has magnetic dipoles from rotating electrons throughout the material that do not cancel out. This means that there's an overall magnetic dipole, which has a north and a south end. These are called poles. All magnets have a north and a south pole because there are no magnetic monopoles. This is a primary difference between magnetic moments and electric charge. The electric field on a bar magnet will always point from the north pole to the south pole, and it'll look like this. Remember that the distance between the magnetic field lines is proportional to the strength of the magnetic field at these points. Magnetic fields can also be generated by charge that is translating, such as a current. Let's look at a current-carrying wire. By the Biot-Savart law, we know that the magnetic field strength, its magnitude, is equal to mu naught I over 4 pi times L over R squared. Thus, the magnetic field decreases by a factor of R squared as you move away from the wire. Let's think about the direction of this magnetic field. You have to use the right-hand law to determine it. It will be moving in a direction like this around the wire. Magnetic fields exert forces on moving charges. If you have a charge Q moving at velocity v through a magnetic field of magnitude b, then you'll get a force equal to QVB sine theta. This means that the force is proportional to the perpendicular component of the velocity with respect to the magnetic field. This force acts in a direction determined by the right-hand rule. In this case, the force will act in this direction. This is always perpendicular to both the velocity and the magnetic field lines. This will cause the charged particle to move in a circular pattern, like this. A similar equation describes the force on a current-carrying wire in a magnetic field. The force in this case is equal to the current times the length of the wire times B times sine theta, the angle between the wire and the magnetic field lines. Here we can see that a wire parallel to the magnetic field will not experience any force. We also briefly discussed electromagnetic induction, which is a phenomenon that occurs when magnetic fields change. For instance, if you place a bar magnet inside a wire loop like this, you will see that as you move the bar magnet up and down, a current is induced or caused within the wire loop. This concludes our unit on magnetism.